Hello students, welcome back to our course Environmental Modeling and Simulation. In today's lecture, we are going to continue our discussion of the climate change and GDP, climate change and prosperity model that was proposed by T.J. Garrett in 2012. So, this is the paper that we are referring to. It's titled No Way Out, the Double Bind in Seeking Global Prosperity alongside Mitigated Climate Change. And one of the major hypotheses of this paper is that lambda is constant, which is basically the amount of energy required to maintain or generate wealth, economic wealth is constant. If we want to continue global prosperity, if we want to maintain global prosperity, then we have to continue consuming energy resources. Obvious objection to this hypothesis could be, what if we stop growing but we just maintain? Since this climate change model is based on very simple thermodynamical principles, which is the reservoirs are at the higher energy potential than the system, which is at second highest potential, and then the surroundings, which are at 3. If we stop consuming more resources, the dissipative forces between 2 and 3 will continue and the system will decay. The example given in the paper is that if an animal, if a human being stops consuming resources, stops consuming food, over time the body will decay. And the same thing is true for the system. Okay. Now, the author, as I mentioned earlier, took the data from past many decades to figure out the value of lambda. And what they noticed was the value of lambda remains roughly the constant. And I mentioned the value of lambda in the previous lecture. They also took the GWP data, the productivity data of last 2000 years, and validated the model and noticed that the assumption that lambda is constant makes sense. So, these are the data points that were available between 1970 and 2008, which were used by the author. One thing to notice is that the global wealth doubled between 1970 and 2008. However, the lambda remained roughly in the same range. So, you see between 1970 and 2008, the lambda is roughly 9.7, and obviously some years it goes up, some years it goes down, but it remains about the same. The other thing to notice is that E, which is the emission, also more than doubled during the same range. Since the global wealth increase and the emission increase both doubled, the ratio of them remained constant, which is lambda C, E by C, 2 by 3, 2.3, 2.4. So, basically, if we want to continue growing like we did since 1970, we will continue increasing our emissions and continue using more and more resources. Now, if we look at these diagrams, there is another very important term that needs to be talked about. One is this term, which is the decay coefficient. It is the rate at which the wealth decays. And then the other is beta. Beta is the wealth, how it drives the productivity. So, obviously, what we want is that beta should be more than the decay. The wealth driving the productivity should be more than the decay in the wealth and thus the decay in productivity. Otherwise, the overall wealth will start reducing. So, beta minus the decay coefficient gives us the return that we discussed in the previous lecture. So, we want the return to be positive. If the return is positive, then the global wealth undergoes an exponential growth. So, basically what we have is dC by dt is equal to return C. Capital C is the wealth. However, if the return is negative, then the global wealth C undergoes an exponential decay. Now, if we look at the data from 1970 to 2008, which is presented in this paper, what we will notice is that the return rate has increased over time, which means our use of wealth to increase our productivity has increased over time, and the decay rate has remained roughly constant, though it seems to be having an upward trend around 2008, but roughly constant. So, this has remained roughly constant. Both the return and the beta have increased over the decades, and then at the end we have I, which is the ratio between the decay constant and the return, which is in the blue line, and that has gone through wild fluctuations over the decades. Okay, in the next figure we have the same figure, but what we are looking at only is not just the decay constant and beta, but we are looking at decay constant C and beta C. So, basically not just the rate at which the decay constant and beta are changing, but the rate at which the overall destruction of the wealth and generation of new wealth are changing. And if we notice this, then it's actually quite similar to the graph that we saw here in the previous one. Now, remember that both of these graphs were drawn while accounting for inflationary pressures. So, inflation has been accounted for this. Okay, as I mentioned, we are going to discuss C-therm. So, let's look at C-therm. This is our C-therm model. C-therm is an abbreviation of the full name of the model, which is the Climate and Thermodynamic Economic Response Model. The first thing we need to understand about the C-therm model, the Climate and Thermodynamic Economic Response Model, is that the generation of wealth is equal to return C, which we already discussed here. The next thing we need to understand is that, so if we look at this model, the diagram that's here, if we look at it, the wealth is used for generating more GDP, for increasing GDP. And there is some destruction that happens, and the destruction in this case we are interested in is not just the natural decay, but also climate crisis induced extreme weather event induced decay. So, for example, because of climate crisis, extreme weather events are becoming more frequent and more intense. We want to account for that damage. For example, recently, because of climate change, the agriculture of many countries in this part of the world, our part of the world, Southeast Asia, was destroyed, which has severely impacted our economy. So, that is your decay. The rate at which you can use your wealth to generate more wealth is beta. We want to 100% use our wealth to increase our GDP, to increase our productivity, which is beta. But then there is this decay constant that comes in. The decay constant is impacted by the resilience of our economy to climate crisis and related extreme events, which here is represented by rho. If the rho is higher, then the decay constant would be lower. If rho is lower, decay constant would be higher. If the rate of return is positive, the wealth is contributing to more GDP. If the rate of return is negative, GDP will become negative, the wealth will start reducing exponentially. Okay, so this is happening on the economy perspective. Now let's look at resource consumption perspective. We are to generate wealth, remember, to generate a unit of wealth, we found out we need a constant amount of energy consumption, heat generation, which is what we studied earlier, and that's where we defined the constant lambda. Lambda was equal to the amount of heat that needs to be generated for a given amount of wealth, and that was 9.7 plus minus something. And this is accounted for inflation, and I think here we have more data. Here lambda is constant, and the unit of lambda is amount of energy megawatts per 1990 US dollar milliwatt. For generating amount of wealth, because this is what's happening here when we go from wealth to real GDP, some amount of energy is consumed. So, energy consumption happens, and that is determined by lambda. Now, when the energy is consumed, the growth in the consumption of energy will also be governed by the rate of return. Some of this energy consumption results in emissions to the atmospheric GHG clubhouse, and here we are focusing on atmospheric carbon dioxide. Some of it is released into the sink. We have carbon dioxide sinks in our environment. Certain forests can act like sink, oceans can act like a sink, but that also results in ocean acidification, which destroys ocean ecology. But anywho, so this is our C-therm model, right? We are trying to use wealth to generate more wealth, and then there is decay of wealth happening, and the decay of wealth because of extreme events depends upon resilience. For generating new wealth, using wealth to generate new wealth, we need to consume energy, and for economies to keep growing, we need to consume more and more energy, as we saw in the previous lecture. The energy consumption results in emission, the red lines here, the red arrows, emission of CO2 and other GHGs. Most of them are released to atmosphere, some of them sink into carbon dioxide. Actually, a very gross simplification is done in this model when it comes to modeling the net carbon dioxide sink. The author says the rate at which CO2 is emitted into atmosphere is equal to net emissions, capital E, minus the rate at which the carbon dioxide sinks into environment, and they are saying this is a linear relationship, so we have a constant here. This is an assumption which is not always true. We still do not understand the carbon sinks completely in our environment. So given the lack of knowledge, this seems to be reasonable for the time when the paper was written, but again the paper also acknowledges that this is gross oversimplification. All right students, this is your C-therm model. Now let's look at what C-therm model says. So when we run the C-therm model, this is what C-therm model notices between 1970 and 2008. So the black dashed lines are the data that we already have. It is very important to see if your model agrees with the data that we already have before we start predicting. Now the blue and the red lines are linking the economic growth with carbon dioxide emission. So the blue one is basically the productivity. Remember, the productivity is economic productivity per year. If you integrate the productivity over the years, you get wealth, because wealth is assumed to be accumulated productivity over many years. So we notice that as the productivity tries to go up, the carbon dioxide concentration, atmospheric carbon dioxide also goes up. And if we look how closely the actual data matches the data that has been predicted, it's quite uncanny. So if you look here, the dark blue line is the predicted data and the dashed black line is what we actually saw. Same here, the red line is predicted data and the dashed line is the actual data. So we know that for the data that we already have, the model seems to work very well. Now let's see how the C-therm model compares with the IPCC SRES model. IPCC SRES model says we can continue increasing the gross world product GWP. Remember, gross world product GWP is basically productivity into 1 year, P into del T. And remember, wealth is basically integration of P from 0 to T, or it can also be written as summation of GWPI over many years. So basically GWP is productivity, and what the IPCC model says, we can continue increasing productivity. So if we can go here in 2008, we are at this amount of trillions of US dollar, we can continue increasing all the way to almost 600 US dollar, trillions of 1990 US dollars per year. And in that case, the atmospheric carbon dioxide will be limited to around 800, little more than 800 parts per ppm. And A1, F1 and A2 are different scenarios that IPCC model runs. But basically, C-therm model, which is in the red lines here, says that the blue lines are gross underestimation of the actual carbon dioxide concentration in the atmosphere that will be if we allow the economy to grow. And notice the economy is not even going beyond this amount in the C-therm model, because the decay becomes more prominent than the rate at which we can use the existing wealth to generate more wealth. So basically your return becomes negative. So economy starts going down. Now in order to read this graph, I need to tell you a little bit more about what's happening here. The green dashed lines here, here, here are timelines. So the first green dashed line at the bottom tells me the situation in 2025. The second one tells me in 2050, 2075 and 2100. The red lines are different case scenarios depending upon resilience. So the gray line here is 0 resilience. Oh, just to clarify, the blue numbers here are inverse of the decay in face of resilience. So when we become less resilient, so let's see here, we are very less resilient. What will happen is, as we try to grow the economy, instead of growing the economy, the return will very soon become negative. Return is equal to beta minus the decay will be so dominant that instead of increasing, our economy will actually decrease. And worst case scenario, the resilience is not very high because inverse of resilience is 5. Worst case scenario, our atmospheric carbon dioxide is still very high. Now if we are slightly more resilient economy, we are decarbonizing, we are rapidly recovering from the environmental disasters because of climate crisis. In that case, if the inverse of a resilience is 1, the concentration of carbon dioxide will be very high, but there won't be some dramatic increase in the overall global prosperity. Business as usual, less resilience, you see the we are looking for economic collapse. Now, all other scenarios, when we are increasing our climate adaptation, we are increasing our resilience to climate crisis and related disasters, all of them have very high atmospheric carbon dioxide values. These situations, very high resilience, very high atmospheric carbon dioxide. So, even though the global economy continues to double and triple, the atmospheric carbon dioxide also continues to double and triple. What this means is that we already know with these high carbon dioxide levels in atmosphere, Earth will no longer be hospitable for most of the life forms as we know them now. Which means that if we increase our climate resilience and continue increasing our economy, it will come at a great cost. The environment will be completely damaged and large swathes of population would suffer irreparably. The ecosystems will be destroyed beyond recovery. So basically, C-therm model is actually quite disappointing in this sense, isn't it? It does not agree with what IPCC says, that there's possibility to continue increasing global world product while not letting the atmospheric carbon dioxide shoot very high. So by the end of the century, depending upon our resilience, according to C-therm model, our atmospheric carbon dioxide will be anywhere from here between 500 and 750 to all the way more than 1000 ppm. Now, this is the same model as was depicted here, but there's a big difference here. Here we are assuming that we are decarbonizing. Now, here decarbonizing was not happening, we were just increasing our climate resilience. Here also we are increasing our climate resilience, going from less resilient to very resilient, but we are also decarbonizing our fuels. And here the assumption is that decarbonization factor C has a half time of 50 years, which is quite reasonable. And what we notice is that IPCC's CIRS model says that, oh, in that case, we can continue doubling and tripling our economy and more while keeping the atmospheric carbon dioxide within reasonable levels. They are not safe, but they are reasonable. The C-therm model disagrees. The C-therm model says non-resilient economy is going to collapse. So, if we are not climate resilient, we are definitely going to collapse. If we are climate resilient, the concentration of carbon dioxide towards the end of the century, 2100, will continue to rise way above what is predicted by the CIRS model. Another thing to note in both these models is that C-therm model says it is impossible to increase the economy beyond a certain value because the decay constants will become very big, which actually is quite reasonable if you look at it. So, here also, even with decarbonization, there is a limit to how much we can increase our economy. Now, basically what this C-therm model is saying, there is a limit to global prosperity and it will come, depending on our climate resilience, it will come at a great cost to the environment. So, basically, even if we become more climate resilient and we want to still continue growing our economy, it will come at great environmental cost. If we go back to the premise of the paper, which says this is a double bind in seeking both global prosperity and mitigating climate change, the model actually does give this conclusion. And so far the data, the GWP data for last 2000 years and the ANC data, which is the rate at which energy resources are consumed and the wealth is generated, the global wealth from 1970 to 2008 onwards, actually does support this model, agree with this model. And the predictions that were done between 1970 and 2008 also match very well. So, model validation seems to be pretty good, pretty well done. And the result here is that we cannot continue seeking global prosperity and mitigate climate change at the same place. The only way out is actually quite disastrous, which is we need both rapid decarbonization and economic collapse to prevent carbon dioxide levels to rise above a particular value. So, if you look at these results of C-therm model, to maintain carbon dioxide at this level, which is above 500 but below 750 ppm, still above the safe value, the only way to maintain here is by getting an economic collapse. So, the economy, instead of growing, it needs to collapse. Here's a fun fact. If you look at this black dotted lines here, this is the data from 180 onwards. From 180 to 2008 AD, so the time at which this model was run. or the data that was available when the model was run. So basically, from nearly no productivity all the way to here is where we are when this model starts. And going forward, the model says the only way to limit atmospheric carbon dioxide from being way beyond disastrous levels is to undergo economic collapse. So this is actually quite a disappointing model in that sense, but it's brilliant because it's very simple. Notice here, when it comes to energy consumption, it is not separating different kinds of fuels. It's not saying iron, which is a different kind of raw material and has different amount of carbonization, or has different amount of carbonization, is different from coal, petroleum, gasoline, which have different amount of carbonization in them. The C is assumed to be constant, and most importantly, the lambda is assumed to be constant, which is A by C. Now, if we look at from the economic perspective, the gross oversimplification is just mind-blowing. And yet, this model works brilliantly. In fact, I encourage all of you to read this paper and try to look at the very well-written discussion, but that's not part of this course, so I'm not going to go over it. Now, from the modeling perspective, if we look at this, basically what the author has done is made a very simple sketch, a very simple diagram of how the system looks like. Now, each of this can be written as ordinary differential equation. For example, we know that from energy consumption to wealth generation, the constant is lambda. So we know very simply that if I want to know the rate at which C is changing, and I know the rate at which A is changing, I can link them through this constant. Now I know that from wealth, existing wealth to productivity, constant is rate of return. So I can very simply write that the rate at which wealth is changing because of this transaction, dC by dt, is basically the constant here, which is the rate of return multiplied by existing wealth. This is an ordinary differential equation that we can write here. Similarly, from real GDP contributing to wealth, we have a very simple system, right? So we have another very simple model. So we see once you have drawn the diagram from this model perspective, you can write the ordinary differential equations, perhaps some integral. Like here I've written the integral, but we can also write this in terms of a differential, because basically productivity is the rate at which the wealth is changing over time. And once you have the equations written down, you can put them together, you can draw phase portraits, which is actually what's going on in the appendix of this paper. That's the supplementary information where the phase portraits were drawn and the analysis was done. And then you can use programs like MATLAB, Mathematica, Octave, R to draw these results, to draw the diagrams, to draw the predicted values and the actual values together. You can put your results using a data visualization platform like R. R has a very good package called ggplot2. Another thing that I want you to notice here is that even though there is absolutely no time element in this graph, we can already, by taking a look at it, understand that whatever changes do happen will happen very rapidly. The next point that you need to notice is that we are plotting atmospheric carbon dioxide, which is one variable on y-axis, and gross world product, which is next variable on x-axis. There's no time element here. So what this is actually is a kind of phase portrait. Now this is not a two-dimensional model, it's a multi-dimensional model. So we can draw different kinds of phase portraits if we are drawing them on 2D. This is also a phase portrait. And the beauty of this phase portrait is that instead of showing the different initial values, the phase portraits that we have done in our class before this model had different initial values. What they showed us was the flow lines, or how the variable will change for different initial conditions. Here the initial conditions are constant, because from 180 to 2008 AD, the black dotted lines here already tell you the path that we have traversed. So instead of drawing the phase portraits or the flow lines for different initial conditions, here the author has drawn the phase portrait for different conditions going forth. One of them is resilience, the other is the year that we are talking about, and then of course the decay factor and the beta are also included. Also, the author has overlapped their results with the results of another model. So, something else that you can do when you do the modeling. Okay, students, so this is all for our course, and I'm really pleased to end our course on this very powerful, groundbreaking model, C-therm model, first presented by DJ Garrett in 2012. To summarize, in this course, we have covered the fundamentals of empirical modeling. We have talked about transportation of contaminants through fluids such as air, groundwater, and we have looked at how different kinds of reactors, both perfect, imperfect, the ones that undergo draw fill cycles, how they change, the models that we write. And one common thing that ran throughout the course for me was using very simple mathematical and basic physics principles like conservation of mass, for example, or in this model, the basic principles thermodynamics, to develop models that are actually representative of very complicated systems. I hope this course is very helpful to you, as helpful as it has been for me. Thank you.